Okay, hello everybody. Am I coming in loud and clear? Let me know in the chat. I've put a poll up asking if you are alive. Now, last week I asked some questions and a lot of people didn't answer, and I took it personally. So if you are alive, fill out the chat, because I'm thinking if you don't fill out the poll, sorry, then maybe I don't know, what are you doing here, right? So play along, even if you're sleepy. And thanks, Steve. Good to know that that I'm coming through loud and clear. Okay. So today's lecture is about Riemann sums. So this is probably something you haven't seen before, but it's kind of old-fashioned in the sense that a lot of people did this a long time ago when calculus was first being developed, but now it's very time-consuming. So we'll show you what it is and how you do it, and then we'll do some examples, right? So let me share my screen with you. Okay, so Riemann sums. So Riemann sums are super easy to sort of represent through a picture. Okay, so suppose I have a function like this, right? This is the graph of the function. And I want to compute the area under this curve, let's say. Okay. Well, one way of doing that is to use a rectangle, right? So let's say I choose this point here as the height, and this is the width. Then this rectangle is almost equal to the area under the curve, right? It's not exactly equal to it, and it's more than this sort of purple area, but it's an okay approximation, right? What happens if we made two rectangles? So we've got sort of the same kind of region, and let's make two rectangles now. Let's slice it in half and make one rectangle there and one rectangle there. Okay, so then we've got the area of this rectangle plus the area of this rectangle. Now you can see, hopefully, that this is going to be a better approximation to the purple area than this. Okay, so this is like the area we want. But adding these two areas together, the green area, is better than that. So what we can do is continue this process until we get really, really thin rectangles that give you an excellent approximation to the area, and you take the limit. So that's really what Riemann sums are about. Okay. Now, if you haven't seen Riemann sums, don't worry about it. The picture is super easy to understand, but there's some symbols and some sums which are not so easy to understand, and that's where the difficulty usually arises. Okay. All right. So I'm going to give you a basic example, right? So let me give you a super easy example. Okay. So who can tell me what is the answer to this integral? If you were given that problem, what is the actual answer? Who can tell me in the chat? It is Russell, right? So if I integrate it, it's 1/3. Yes. Okay. Now that's easy, but a long time ago, mathematicians didn't know this way of working. Okay. They didn't know that you could find the antiderivative and then use the endpoints. They didn't know how to do that. Okay. And so what they did was they used these rectangles to approximate the area under the curve, right? So instead of doing this, which takes, like literally 5 seconds, they did this sort of thing. Okay, so that's what we're going to learn about today. And the basic idea with these so-called Riemann sums is to approximate the area under a curve with rectangles. Okay, so when we sort of draw in these rectangles, we're approximating the area under the curve with the area of the sum of the rectangles. Okay, that's it. Okay, so that is it. So we'll learn how to set them up and calculate the Riemann sums. Okay, so that's the idea of today's lecture. So let me know in the comments, have you ever heard of a Riemann sum before? Farhan, it's a good question. Well, like technically speaking, when you do Riemann sums, you're like, these are the basic building blocks of what's happening here. Okay, so you can learn about it, but you wouldn't effectively use it when you're doing the calculations unless you're absolutely asked to do it. It's very similar to the epsilon m definition of a limit, right? You wouldn't use this every time you're computing a limit. You would just do it. But this is like the foundation for limits, right? And Riemann sums are the foundation for integration. Does that make sense? Yeah, good. So from a practical point of view, they take a lot of time, but from a foundational point of view, they're really interesting. Okay. All right. So here comes the crazy notation, but don't be too worried, because I'll give you some examples and we can talk through it. Okay, so you've got an interval on the x-axis, and what you do is you slice it up into bits, right? Just like we took this interval and we sliced it up into 2 bits, right? Here we had 1 bit, here we have 2 bits. Here we have n bits or n segments, right? And what we're going to do, each of these segments are going to be the base of our rectangles, okay? So this is the base of one rectangle, this is the base of another rectangle, okay? So this is just a fancy way of splitting up an interval AB into equal segments, all right? And suppose we've got a nice friendly function. If we can determine the maximum and the minimum of your given function on each of these little intervals, then the lower and upper Riemann sums are given by these things here. Okay, so if I go back to my original picture, I've split this interval up into 2 parts. On this interval, there's the maximum of f. On this interval, there's the maximum f. On this interval, there's the minimum of f. And on this interval, there's the minimum of f. Okay, so when you're looking at these kinds of definitions, you're looking for the maximum of your function on each little subinterval and the minimum of your function on each subinterval. And these are basically just summing rectangle areas, right? This is the base of each rectangle and this is the height. Okay, this is the base, this is the height. And the sum means you're just adding up all the areas, right? So for this one, we'd add the area of this rectangle plus the area of this rectangle to get the upper Riemann sums. Okay? So that's pretty much it. It's just rectangles. People get a bit frustrated with this notation, but just think of it, base times height, and you sum up the areas of the rectangles. That's all that happens. Okay? That's the way I like to think about it anyway. All right, let's do a real simple example, and we can work through it together. And I'm hoping that this is a good example for you. Okay? All right, so you've got a function x squared. We've got an interval 0 to 1, and we want to set up this partition with 4 subintervals. Okay, so I've got my interval 0, 1, and this subscript says, okay, you're going to break it up into 4 subintervals. Okay, in this case, they're all going to be width of 1/4. Okay, so b minus a on n, which gives you the width, is 1/4 here. Okay, so you've got your function, you've got your interval, you've got the width between each point, and now we're asked to set up the Riemann sums, right? So we want to look for the maximum of our function on each subinterval and the minimum of our function. So let's do that separately. Okay, so I'll do that over here. So here's our function. Okay, and let's say here's 1, here's a half, 3/4, 1/4. Okay. Let's go for the lower. This is the lower Riemann sum. So we want the minimum points. Okay. So if I'm on the interval 0 to 1/4, that's the first bit. Where does the minimum value of f occur on the interval 0 to 1/4? Who can tell me? Who can tell me in the chat? If I'm on this interval, yeah, Abdul Rahman, it occurs at 0, right? So x, so this is like the first one, minus equals 0, and f of x1 minus equals 0 squared, because we squared a function, which is just 0. Okay, so now what we do is we can do that for every other interval. From here to here, the function, the minimum value occurs at 1/4. Yep. Okay, and so you can continue that. You've got 2 more to go. Okay. So what you can do now is set up your Riemann sum here. This thing is going to be 1/4. This is going to just be the function at the left-hand endpoint, okay, of each of our P. Okay, so it's going to be this. 4, I equals 1. It's going to be xi minus squared times 1/4. So all I've done there is I've replaced f with the function, the squared, and this is 1/4. Okay? So what you can do now is, if you want to, you can just write this out. So the quarter is not going to change anything. So you're going to get something like this, right? 0 plus a quarter squared. What's the next one? On this interval, the minimum's occurring there. And on this one, the minimum's occurring there. Okay. Now, if you work that out, I get something like 7 on 32. Okay. Let's just take a minute and compare that with, say, the integral of this. Right, we already did this. This is ultimately what we're working towards. Okay. Now, this is much less than this. Okay. 7 on 32 is not a very good approximation. But if we took more little sub-intervals and sub-rectangles, we'd get a much more precise answer. So that's the lower Riemann sum. Let's set up the upper Riemann sum. Okay, so now we go back to our intervals and we look for the maximum. So who can tell me, on this interval, where does the maximum of our function occur? Who can tell me in the chat? 1/4 is absolutely correct. Okay, so x1 plus equals 1/4. And so f of x1 plus equals 1/4 squared. Okay, so then we move on to this interval. The maximum occurs on this interval at 1/2. Okay. So the maximum there will be 1/2. Okay, so now let's get this upper Riemann sum. So this upper Riemann sum, you've got the maximum value here times, it'll be times 1/4. Okay. Okay, so the 1/4 doesn't change anything. We can just bring it out the front. And what will we get here? Well, we're going to get 1/4 squared plus 1/2 squared plus 3/4 squared plus 1 squared. Okay. Now you can kind of see here that this is almost the same as this, except for that term, which is kind of interesting. Okay. If you work this out, you'll get something like this. Now, let's compare this with this. This is much greater than this. Okay. But again, if we took lots of little sub-intervals, this would be much closer to this. Okay. So just a little note that the upper Riemann sum equals the lower Riemann sum plus 1/4. Why is that important? Because if you calculate one of the sums, you can use that to get the other sum sometimes. Okay. All right. So before I go on, let me just pause, because this is quite technical mathematics, right? So if there's something that you want to ask about the example that we've just done, please, the time is now, because this is not an easy example. The notation is difficult, and it's a bit fiddly. So hit me up in the chat if you have any questions. Okay. Now you could say, well, what have we actually calculated there? Well, I'm glad you asked. Let's look at this. What does this actually represent? Well, you've got a rectangle with 0 height, a rectangle with that height, a rectangle with that height, and a rectangle with that height. So this is that area plus that area plus that area plus that area. Okay, that's what this actually is. It's just a sum of rectangle areas. Okay, and what is this? Actually, let me do that in a different color. What is this? That is that area plus that area plus that area plus that area. Okay? And so what you can do, if you take lots and lots of subintervals, you can squeeze these together and the two areas actually merge. They merge together. Oh my goodness. Yeah, Nicholas, you can do that if you want a stronger approximation. I think that they do that in things like trapezoidal rules and things like this. Okay, so you can use the average of the two, not a problem at all. That'll give you probably a better approximation. We'll be interested in what happens when the n's go to infinity. Okay, so what happens when the number of points in this interval go to infinity? That is the question. Okay. Abdul Rahman, for increasing and decreasing functions, I think what you're saying is true, but it's not necessarily true for other functions. Okay, so this is like a little time saver if you have an increasing or a decreasing function. Okay, all right. So Steve, so we get many rectangle areas, and if we let n be much bigger, we can assume we get the correct area. Correct. Yep. Well, the limits have to exist. So when we take these limits of these as n goes to infinity, we want both of these things to converge, like to give us some number, and we want the two limits to be the same number. Okay, I'll do an example in a minute. I'll do an example in a minute. Alan, yes, the smaller the interval, the better the approximation, but the more computation, right? The more computation you have to do. So that's the tricky thing. Okay. Yeah, it is, Abdul Rahman. When you're taking the limit as n goes to infinity, that's exactly what you get. So I'll show you on the next page because there are some really good questions here. So let's go back to our x squared function. Okay. Now what they're asking us to do is to set up the lower and upper even sums on this for any n. Okay. So what you can do is, just like we did back here, instead of this, we can get this. Instead of 1/4, we're going to get 1 on n. And what's happened here is this sum has been simplified. Okay, so this is where this nice simplification comes from. Let's see what happens when we try to simplify this as n goes to infinity, right? What are we going to get? Well, we're going to get 1/6. Okay, let me just get my notes here. If we divide this n cubed into the n and n squared into the rest of it, you'll get something like this. Okay, so you can divide that into the first part. Now, what is this going to happen as n gets large and positive? That goes to 0, that goes to 0, you get 2/6 as n goes to infinity. Okay, so that is actually, remember, it's the exact same thing as this. Wow, how about that? Okay, so with all this work, which is not very efficient, And this is what people used to do back in the day. They would work out these sums, simplify them, and take the limit. Yeah. Okay. And then for the upper Riemann sums, well, that's pretty much the same as we were doing before. That's the width of your base. That's the sum of the heights of the rectangles. That simplifies to this, and this also goes to 1/3 as n approaches infinity. Yeah, Nicholas, it's a bit tricky. The sums are usually given to you via induction. Okay, so if you look in the let me see if I can pull it up. In the that's usually the hardest thing. Okay, but you're usually given some sort of hint there. Let me just see if I can find the notes. Calculus notes. Here we go. Okay. So let me just go see if I can find it here, because it's a really good question, right? Yeah. So let me just have a look here. I'm just going through back to the end of the chapter. So just bear with me for a second. Clicking, so much clicking. Yeah, okay, so let me just show this to you now. So you can see in your workbook, they've got this, right? And then you may need that. So they give you a friendly hint, right? But if you're finding the Riemann sums of x cubed, you may need that. Okay. So my interpretation is you're not expected to come up with these things on your own. But if you're asked to do these Riemann sums, you'll get a hint. Does that make sense, Nicholas? Yeah, I know. It's all magic, Steve, I know. All right. Okay, so the most important thing I think here is that once you get these values, they need to be the same. Okay, if they're not the same, then you've either made a mistake or the thing is not Riemann integrable, right? Okay, so this is the very old school OG way of performing integrals. Now we will see a much faster way of doing these problems, right? I mean, seriously, who would ever do this if you know the fundamental theorem of calculus? Only original gangsters, probably. Old school. Yeah, Abdul Rahman, I think you're right. You definitely need it. Okay. So there's that's a big hint. Yeah. So if these things are not equal, then the integral doesn't exist. Okay, it's not well defined. If one of these doesn't exist, then the integral doesn't exist. Okay, so let me give you a summary sheet on how you bring all these ideas together. Okay, so the method or the ideas is partition is just a funny way to say slice up. Okay, so when you talk about a partition, we're talking about, say 0, 1, it's sliced up into little bits. Okay, like you're slicing a loaf of bread. Okay, you set up the upper and lower Riemann sums, looking for where f achieves its maximum and minimum values, right? So the maximum is like that, and the minimum is like that. Okay, on each little subinterval. All right, so this one would be x1, x2, blah, 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 xn. So once you have those, You simplify the sums and then take the limit. Okay. If the two limits are equal, then we denote the joint value by this thing. And if the function is non-negative, then you can talk about the area under the curve. Now, it's a slow, painful way of doing it. Okay? Painful. Yeah, it's pretty painful. So luckily, we have other ways of working. But like I said, a lot of people, this is what they did back in the 1600s. That was Riemann sums was their thing. Okay. Oops, hang on, that's the wrong button. All right, there's a question in the chat from Abdul Rahman. When you how do we check that it actually doesn't exist and not that we made a mistake? Well, the kind of functions you get are usually the friendly functions, right? So this function is x squared. We already know what the answer is going to be. It's going to be 1/3. So if you take these limits and you don't get a third, there's obviously a problem. Okay. And if you look at the types of functions that you see in the course pack, let me just go over there again. I mean, these are all pretty well-known functions. 1x, x squared, x cubed. Okay, so you kind of know what the answer should be anyway, right, for these kind of problems. Okay. All right, so that's a lot to take in. Let's just go back. I'll just break it up a bit now. Let's see if we can have a look around. Oh, can anyone see the dog hiding? That's my puppy. Can anyone see her? Let me know if you can see her. All right, back to business. Oh, I know, she's black as night. Maybe she'll come out later. She's really black. I end up stepping on her all the time, unfortunately. I just can't see her. All right, so as you've all seen, the process of evaluating a Riemann integral or a Riemann sum is not fast. Okay, yeah, it's a she, Steve. Yeah, little. Her name is Minnie. So we will see a much quicker way of doing this later. And what's the quicker way? Well, the quicker way is just the fundamental theorem of calculus, right? So if you have, I don't know, an integral like this, you find an antiderivative of x squared, right? And then you put it in and you evaluate the antiderivative at the endpoints. Okay, so that's your answer. You can simplify this, right? It's going to be something like 7 on 3 or something. Okay, easy, right? Easy. The fundamental theorem of calculus. We'll learn about this in the next lecture. But of course you would do this rather than do all this, okay? But this is just sort of letting you know where the ideas come from and how they're formally used and historically used. Similar to the epsilon m thing that we did with limits. You wouldn't use this for everyday limit evaluation, but it's helpful to know that there's some structure there. All right, a couple of interesting examples. Not all functions have an integral. Okay, so for the rational numbers, right? So when we talk about rational numbers, it's like 1/2 -3 on 2, 10 on 7, those sort of things. You've got a form like this where a and b are integers. Okay, so something like this, pi is not a rational number. √2 is not a rational number. Okay, because they can't be expressed like this. All right, so if we're integrating this function, it's 1 for all the rational numbers between 0 and 1, like this, for example. And it's 2 for all the irrational numbers. Okay? So this has a lot of discontinuities. And the most important thing here is that this is a function that where the integral doesn't make sense. Okay? And why doesn't it make sense? Well, it's because the lower Riemann sum and the upper Riemann sum are not equal. Okay? The limit, sorry. Okay? So you can see in the previous example, we took these limits and they were both equal, right? For this example and this interval. That was fine. But for this one, the limits actually doesn't make sense. I think the lower limit is 1 and the upper limit is 2. Okay? I think it's something like this. I think that's what it is. Okay? So this is a situation where if you wanted to integrate this, you can't actually do it, right? So now we're breaking the Riemann integration. And the most important thing here to know is that highly discontinuous functions may not be Riemann integrable. Oh. Okay. So this is one kind of function that has an infinite number of discontinuities. I mean, you can't even draw this function. It's so that there are so many discontinuities, you can't even really draw it. Yeah, it's pretty hard. Okay, because it's sort of just as soon as it's 1, if you move a tiny bit to the left or the right, it becomes 2, and then you move back, it becomes 1 again, and then it moves back, you move again, it becomes 2. So this is a really crazy function. Okay, but this is the most important thing. If you have a function that has too many discontinuities, then it's not Riemann integral because these two limits don't exist. Okay, so let's look at another example. What about this one? Okay, you've got the integral from -1 to 1, and the question is, why doesn't the following Riemann integral make sense? Okay, can anyone suggest why a Riemann integral for this doesn't make sense? Any ideas? Any ideas? Yep, that's definitely a problem. Yep, the discontinuity is so huge. Yeah, Bailey, that's also an important. So the discontinuity is so huge that there's no way. I mean, if you wanted to set up the Riemann sum, how would you do it? I mean, the closer you get here, you can't really get the maximum when this shrinks down, right? So there's a big problem with this one as well. Okay, so I would say that the limits do not exist. So the limits of the Riemann sums. Okay. So this is another kind of different discontinuity. Oh, hang on. Let's go. Let's go. No. Okay. But if you have a nice function, they're bounded and a finite number of discontinuities, then there'll be Riemann integrable. Now, for most of the functions that you'll see, let me just go back to your notes here, your class notes. The functions that you'll see, they're all friendly continuous functions. They're polynomials, in fact. Okay, so I don't think you're going to get really any surprises for the functions that you see in let's say you get an exam question on this, right? All right. Properties of the Riemann integral. Just make sure you've got a plus sign there. I think I had a different sign in your notes, so just make sure you have the right thing there. These are all the properties that you would expect. And of course, you would know that these are true. I mean, just from what you've learned at school. So, for example, in star, if you're integrating x squared from 1 to 3, it's the same as integrating x squared from 1 to 2 and then adding the integral from 2 to 3. Okay? If you're integrating between the same point, you get 0 area. Okay? If you swap the order of integration, you change the sign. Okay? But be careful. Let me just put something underneath that. If you have the integral of a product, it doesn't equal the product of the integrals. Okay? So even though these are sort of nice standard ideas, you can't always get what you want with them. Okay? All right, folks, we have a few minutes to discuss anything you'd like. Did we want to talk about the assignment, or, how is everyone going with the writing assignment? That's the last slide for today. If anybody wants to, let me just, session settings. People can share their video, share their audio. How are people? Abdul Rahman, yes. What is your random maths question? Hit me up. The more random, the better. If anybody has any questions related to the writing assignment, then feel free to, yes, Steve, you're right. So there's this meme, right, where, let me just see if I can find it. There's a meme that says you basically spend, here we go, this is it. Here we go. Let me just have a look. I'm just going to show you this. This is it. Let me see if I can. Okay, time spent on computer during school. Blue area, time doing the actual assignment. Orange area, typing random stuff and searching it. So I think for maths, it's probably doing the typesetting, right? Doing the typesetting. I think that's probably what everybody struggles with. Abdul Rahman, is every differentiable function integrable? Yes, I would think so. I think that every differentiable function is integrable because if it's differentiable, then it's certainly continuous, and every continuous function is integrable. Okay. Um, every integrable function is not necessarily differentiable. Okay. Like you could have a function like this, right? Where let me go back to my thing. So the first part of your question is the answer is yes. The second part, let's say I have a function like this, like a split function. Okay, and it's between 1 and -1. That function's definitely Riemann integrable, but you can't differentiate it at this point. Okay, so the answer to your second question is, well, no, it's not always true. Okay, so it's not vice versa. Nicholas, mean value theorem is it's an approximation. It's an existence theorem. Linear approximation, it approximates something. Okay, so they're trying to do two different things. But what you can do with the mean value theorem, you can use it to approximate other things in a linear fashion. Okay, so yeah. So mean value theorem is an existence theorem. It tells you there's a C such that f dash equals whatever, whatever, whatever. And linear approximation, I think what you're doing there is you are using a tangent line to approximate a function. Yeah, but you can also use the mean value theorem for something else, like approximating errors and things like that. All right, Eloisa, do all the assignment only include calculus question? Oh, your chosen flavor includes calculus. Which one did you choose? Which flavor? Tell me what's your flavor, Eloisa? Which one did you do? Electronic things. Okay. Electronic things. I'm not sure what that means. Economic? Do you mean economics, Eloisa? So I'm not sure if they all include some algebra and some calculus. But yeah, I don't really know because everybody's assignment is slightly different. The questions are slightly different, right? Chemistry. How was chemistry, Aiden? Did you enjoy it? Have you finished it? Should I do a tutorial today about the assignment? What should I do? You tell me. All right, let's do that today then. Let me ask a poll because we've got 2 minutes. Should I do a tutorial about the assignment today? Let me know, people. Let me know. Oh, 18.3. More people are responding than when I asked them, are you alive? Ooh, lots of yeses. It's very exciting. I don't know where Captain Bill is. Hawk, I have one at, let me just check. I have one at 2 p.m. Sydney and 4 p.m. Sydney time. So let me just write it down. See you at 4 p.m. Hawk. Thank you. Where is Captain Bill? Captain Bill, where are you? Maybe he's off flying the plane somewhere. Oh, Captain Bill, hello. You've just snuck in there.
I was having a little trouble connecting, but I'm here now.
Ah, well, we thought that you were delayed due to unforeseen circumstances. Like they announced at the airport, due to the late arrival of the plane or something.
No.
Hey, Carl, you can come at 2 p.m., buddy. 2 p.m. Bill, do you remember a couple of years ago, we did some tutorials about giving feedback for the writing assignment? So I'm just asking everyone if they want to do that today. And a lot of people have said yes.
Yeah, we did that last year in our tutorials. I think it was, I would hazard a guess, it was the week 7 tutorial, because obviously it was, but it could have been, depending on, I can't remember exactly what time our tutorials were, but it was either week 7 or week 8 tutorials. And we may have recorded it. I can't remember.
No, I don't think we did because people were sharing their assignments and we didn't want to record that. And the other thing is the writing assignment is due on Monday, I believe. Or no, Tuesday, week 8. Yeah. So I think I might do some this afternoon.
That sounds excellent.
Well, Carl, you can also come on Monday, buddy. I've got another class on Monday. So I can also talk about the assignment then. Okay.
And I've got a online consultation directly after the lecture, and more than happy to critique what you've written.
Yeah, that's the idea. Yeah. The idea is that you show us the work and we can give you some feedback. I think that's how it worked last year, wasn't it, Bill?
Yeah. People shared and they were happy to share their responses, and then we gave a bit of feedback on it to help improve it.
Yeah, I'm just going to put this in the chat. I don't think that we will not be recording for assignment feedback. And the reason is that people will be screen sharing their work and we don't want to share that due to privacy. Okay, I'm going to hand you over to Captain Bill, everyone. Thank you and enjoy your flight of algebra with Captain Bill.